From across the globe, from the center of aerospace, and now to you.
Thank you for downloading the Aero Society podcast from the Royal Aeronautical Society.
Good afternoon, everyone. Welcome to today's Royal Aeronautical Society Heathrow branch webinar. My name is William Lee, and I'm the Honorary Secretary of the branch and the moderator for today's session. Joining me today is our speaker, Dr. Luke Storer, and our Vice Chair, Dr. Anna Pedras, who will be hosting today's webinar. Before I hand over to Anna, there are a few housekeeping items that I would like to make. First of all, please feel free to share your thoughts about today's event on social media channels such as Twitter, by @RAESLHR and using the hashtag RAESLHR event to interact with us. Secondly, if you require a CPD certificate of attendance for your own initial or continuing professional development records, please use the Q&A panel now to inform us your name, and we will email this to you post-event. Your microphone is on mute, but throughout the webinar, we do encourage you to use the Q&A panel to raise any question that you may have, and you can also interact with us by clicking the like button next to each questions that are being published. Finally, I would like to make you aware that today's session is being recorded and will be made available via our podcast and YouTube channel post-event. Without further ado, let me hand over the floor plate to Anna.
Thank you, William. Good afternoon, everybody. And again, thank you, William, for that introduction. My name is Anna Pedras, and I'm the Vice Chair of the Heathrow branch of the Royal Aeronautical Society. And in my day job, I am a lecturer in responsible management and sustainability. So I am particularly delighted to welcome Dr. Luke Storer as our guest speaker in our October lecture on the topic of the impact of climate change in aviation. Welcome, Luke, and it's a pleasure to have you here with us. Luke Storer studied meteorology and climate at the University of Reading, covering topics such as atmospheric dynamics and climate change. During this time, he was also a player and a coach of the university's American football team. He then went to spend a year in the United States at the University of Oklahoma, covering a variety of topics, including radar meteorology, synoptic scale meteorology, and computer simulations. And in his spare time, he actually participated in numerous storm chases. In Luke's final year, he was able to bring together his two passions, meteorology and aviation, by researching the impact of the North Atlantic Oscillation and the El Niño Southern Oscillation on the jet stream and the potential impact on transatlantic flight times. Following on Luke's undergraduate master degree, he actually went to complete a PhD at the University of Reading. And again, he was able to combine meteorology and aviation by examining the impact of climate change on clear-air turbulence, and by designing a new way of forecasting turbulence with the Met Office with the aim of improving aviation safety. I have been told that there were 6 scientific papers from his PhD, and that must be some kind of record that will be really hard to beat. So in January 2019, Luke decided to move from academia onto the industry, and he has been working since as a data science consultant for British Airways, focusing on their strategic partner alliances. So Luke, it's a privilege to have you here with us. Welcome to the Heathrow branch. We are eager to hear your talk, and well, we are ready when you are. Welcome, Luke.
Thank you very much, and thanks very much for the invitation. As Anna said, I've been working for British Airways for a year and a half now, but I've been invited here to talk about the research that I did at the University of Reading. And this was in conjunction with Professor Paul Williams at the university, and also in conjunction with the Met Office and Dr. Philip Gill, who helped, and they were both my supervisors during my PhD project. So as Anna said, I'm going to be talking about the impact of climate change on clear-air turbulence, and then also trying to examine a new way of forecasting turbulence. So an overview of the talk. I'll just give an introduction to turbulence and its impacts on aviation. Then an important question that we've been asked when doing climate models is, can climate models predict clear-air turbulence? And then following on from that, we'll have a look at how climate change is going to impact clear-air turbulence in the latter half of this century compared to pre-industrial control period. And then this will provide ample motivation for us developing a new forecasting technique, which is a multi-model ensemble using a single diagnostic and then multi-diagnostics, which I'll get into later, and then I'll close with a summary. So in introduction to turbulence, it's well known by most people. Anyone that's been on an aircraft will know what turbulence is. They've experienced it themselves. And it can range on scales from hundreds of kilometers down to less than 1 centimeter. However, approximately 100 meters to 1 kilometer is the size of the turbulent eddies that impacts aviation, because anything larger than that, the plane would just fly through it. Anything smaller, then it wouldn't impact any of the aircraft. So the problem with having the turbulence on a scale of 100 meters to 1 kilometer is it's generally smaller than the numerical models that we use to forecast. Therefore, we have to use turbulence diagnostics to infer the location of turbulence based on larger scale dynamics. And this isn't perfect, which is why we believe that a probabilistic forecasting technique would provide more information. And as I say, I'll get onto that later. Turbulence can be dangerous. Objects that are unsecure can be thrown around in the cabin, especially passengers if they're not buckled in. This is why it's particularly dangerous for cabin crew, because they're generally up and about serving drinks or the food meal service, and these are generally people that are most at risk if you encounter severe turbulence. So I would always recommend that you wear a seatbelt if you're in the cabin, regardless of whether the seatbelt sign's on or not, just to be safe of any unexpected clear air turbulence. And the impact on aviation, it costs the industry millions of dollars each year, paid out in compensation for people that have been injured, but also due to lost working hours from cabin crew. Because if a cabin crew member was injured during a flight, they're then not able to work for a period of time, and then that costs up to 7,000 days per year in lost cabin crew time. And most of these injuries occur above 10,000 feet. As generally the seatbelt sign is switched off, because during takeoff and landing, the seatbelt sign is generally switched on anyway. So above 10,000 feet, when there's no expectation of turbulence, the seatbelt sign's off, and that's potentially where injuries can occur. And I've just highlighted some examples here. There was an American Airlines flight that was diverted to St. John's with injured passengers, and then an Air Canada passenger aircraft a few years ago that suffered 40 minutes of turbulence. So it happens fairly regularly where planes are having to be diverted due to any encountering severe turbulence. So what are the sources of turbulence? There are two that we don't really get on here, which is boundary layer turbulence. So this is, if you've ever experienced coming into land, it gets a bit bumpy nearer the ground. That's boundary layer turbulence, but generally the seatbelt sign is on for that portion of the flight. And then there's in-cloud turbulence, where if you've ever flown through a cloud, you would notice that it gets a little bit bumpy. But again, pilots are able to visibly see a severe thunderstorm and therefore avoid it, or can see it based on onboard radar. Whereas clear air turbulence, which is in a region devoid of any clouds and cannot be foreseen by the pilots, is the one that is potentially most dangerous. And this comes from mainly three sources. The first is the convection itself. If you have deep convection, this can produce gravity waves, and these gravity waves can propagate far away from a cloud into a region devoid of cloud. And in this location, this could be where they break and then turn into clear air turbulence. And similarly to this convective turbulence, you also have mountain wave turbulence. So large mountains can cause gravity waves, such as if you're flying over the Rocky Mountains, you might experience mountain wave turbulence, or on a transatlantic flight flying over Greenland, where there's some large mountains, you might experience mountain wave turbulence. And again, it's similar to the convection, where you have gravity waves that propagate into clear air and then break and form turbulence. But the one that is probably most prominent is wind shear turbulence, and this is caused by the jet stream. So the jet stream is a fast-flowing river of air in the upper troposphere, lower stratosphere particularly, where you have strong wind speeds, it can create vertical and horizontal wind shears, and it's these shears that potentially will form turbulence, and that's one of the main sources of turbulence that we forecast. So we categorize it on a scale from light to extreme. Light is what most people would experience on any day-to-day flight, a slight strain against the seatbelt. Moving through moderate, where you can definitely feel a strain against the seatbelt. Unsecure objects such as drinks might be displaced. But then severe and extreme turbulence is where passengers and any unsecure objects might be thrown around the cabin. And this is the type of turbulence that we mainly need to focus on forecasting, because this is the one that would potentially cause injury to passengers and crew. So, as I said, one of the main questions that we got when doing some of this climate change analysis is how do the climate models perform in forecasting the location of turbulence? So we conducted an analysis that compared the climate model data from the Met Office's HADGEM2 Earth Systems output model compared to a reanalysis data set from the European Centre for Medium Range Weather Forecasting. A reanalysis data set is one where it's almost like the best guess of what has historically happened. It's based on numerical simulations combined with actual Earth observations. So by comparing the climate model to what is the best estimate of what actually happened, we can compare and contrast and see how similar the climate model performs compared to the reanalysis data set. And we did this for 7 turbulence diagnostics in all 4 seasons and at 2 separate flight levels at 200 hectopascals and 250 hectopascals. This is equivalent to about 33 to 39,000 feet. So cruising altitude for commercial aircraft. So the comparison, as I said, is the HADGEM2 ES, which is the climate model that we used, which has a lower horizontal and vertical resolution. So then the reanalysis data set. So we regridded the reanalysis data set to be on the same horizontal and vertical scale as the climate model, but also left it on its native grid as well to compare the impact of resolution on the forecasted turbulence. So we compared the global distribution, the percentage change distribution, so where the historically turbulence has changed, and also where what the percentage change is. So is the climate model over or under forecasting the percentage change? So this is just an example diagram comparing 2 of the turbulence diagnostics. So on the top 3, we have the Coulson-Panofsky index, and on the bottom we have the LROD and NAP turbulence index 1. And the bottom index is one that has been used by the Met Office to forecast turbulence for many years. And we can see that on the left of the 3, that's what the climate model predicts as the location of turbulence. In the middle, if you're moving left to right, is the reanalysis data set regridded to be on the same resolution as the climate model. And on the right-hand side, we have the reanalysis data on its native grid. And what I think we can see, especially in the LROD turbulence index, is that the climate model performs extremely well in forecasting the location of turbulence. You can see where the storm tracks are over the North Pacific and also over the North Atlantic. It might under forecast in some regions, but generally the spatial distribution is pretty good. For the Coulson-Panofsky index, which is on top, the climate model performs well, more in comparison to the reanalysis data set on the same grid, whereas the reanalysis data set on its native grid has a slightly different spatial distribution. And then this suggests that the resolution does have plays an important part in forecasting of turbulence. And this would be something that we suggest would require further analysis. But we were satisfied that the climate model predicts the location of turbulence pretty well. And actually, the largest difference in the location of turbulence is which turbulence diagnostic we've used. So the Coulson-Panofsky index forecasts turbulence in a completely different location to the LROD index. And we thought that was quite a big revelation, that the climate model is less of an issue than which diagnostic you think predicts turbulence the best. So this was an example for December, January, February, so the Northern Hemisphere winter. And we can also compare the same for June, July, and August, which is the Northern Hemisphere summer, which is winter for the Southern Hemisphere. And you can see, again, the climate model performs reasonably well, particularly when it's on the same resolution grid. And again, it's the spatial distribution between indices that is the largest discrepancy, rather than whether we use a climate model or the reanalysis data set. Now, here's a plot of the percentage change in turbulence. So this is a comparison between the first half and second half of the data period that we looked at. And we can see that the location of forecasted change, particularly around the equator, is much larger in the reanalysis data set than in the climate model. So this suggests that in any further study that we do, and in the climate change modeling that we conducted, we might be underestimating the change in turbulence around the tropics, around the equator. But if you're looking more towards the mid-latitudes, for example, the climate model performs better, but obviously the exact location is not perfect, but again, it might be a slight underestimate. And again, this is for summer, the previous was for winter, Northern Hemisphere winter, this is Northern Hemisphere summer. Again, an underestimate around the equator. But generally, the reanalysis data set is forecasting darker red, which means a larger percent change. And again, this just highlights the fact that the climate model might be underestimating it might be more sluggish in modeling of the climate change impact on turbulence. So in summary of this, climate models can predict the location of Clear-Air turbulence, and the main uncertainty comes from which diagnostic to use and not which model that we might use. And there are larger increases in the reanalysis data that show any estimates that we make in a climate model may be underestimated. So following on from that, we did conduct a climate change study. This was following on from work that Professor Paul Williams had done at the university already. He looked at a study of the North Atlantic, so we expanded this further to see whether climate change will impact turbulence globally in all seasons and at multiple flight levels. So we used the same climate model as before, the HADGEM2 Earth Systems climate model from the Met Office, comparing a pre-industrial control base, so before the Industrial Revolution, compared to RCP 8.5. This is the high emission scenario based on the Intergovernmental Panel on Climate Change, their highest emission scenario. Obviously, this is subject to social political debate as to whether we should use a different scenario, but we chose the highest emission scenario to test for sensitivity. So we looked at 20 separate turbulence diagnostics and set a threshold and counted the number of hits above this threshold. Then when you compare the pre-industrial control to the climate change scenario, if we see more hits above the threshold, then we would say that there's more frequency of turbulence events, and therefore there's more turbulence based as a result of climate change. And again, we looked at 4 seasons and 2 flight levels and calculated the percentage change between the 2 time periods. So here's just an example of 6 of the turbulence diagnostics that we looked at. And red indicates a percentage change increase in turbulence, and blue indicates decrease in turbulence. And all of these turbulence diagnostics are mainly focused around the jet streams. So the jet streams, as I mentioned before, is a fast-flowing river of air, and it happens around the mid-latitudes. Particularly, it impacts transatlantic flights and trans-Pacific flights. And we see that over the North Atlantic, there's a clear increase in turbulence in all of the diagnostics, which would impact all of the flights between Europe and North America in the future. And we see that these increases are also statistically significant. So where we have a dot, that says that the results are not statistically significant. So we see that where we see the dark reds and even the dark blues in the tropics, it's statistically significant. But as mentioned before, in the tropics, we're not showing that increase here, that may actually be present that the climate models are just not able to pick up. So what we did is we combined all of the 20 diagnostics, assuming that each turbulence diagnostic was equally likely to be true. So just did a simple average of the percent change for each grid box. And we see, again, the North Atlantic, Europe, North America sees a very large increase in turbulence, over 100%, which means that it would double compared to the pre-industrial control period. And also we see in the Southern Hemisphere around the southern jet stream, again, large increases with an expected increase in wind speed to the jet stream, and therefore changes in the turbulence as a result. So just to highlight some of the percent changes, we looked at the North Atlantic and Europe. So we have 5 turbulence strength categories: light to moderate, moderate to severe, and then severe. At the 2 different heights in the atmosphere, 200 hectopascals being about 39,000 feet, 250 hectopascals being about 33,000 feet. And we see that in general, the more severe the turbulence, the greater the increase in frequency. And as we said right at the very beginning, severe turbulence is one of the more dangerous and potentially harmful to passengers and crew on board. And it's expected potentially over the North Atlantic at the upper flight level to be 185% increase. This is essentially a tripling of turbulence compared to the pre-industrial control. And this is true also of Europe, and is true also around other parts of the world, but I've only highlighted these 2 here. So just to summarize, turbulence is set to increase with climate change. That was known before from previous studies, but this is expanded to be not just moderate turbulence, but all turbulence strength categories at multiple flight levels and around the world. And the increase is strongest at the higher flight altitude, so 39,000 feet. And we wanted to provide some context as to what this would actually feel like, because saying that there'll be a doubling in turbulence doesn't necessarily mean anything to anybody that doesn't fly regularly. So the context is, in winter, severe turbulence by the middle to the second half of this century will be as common as moderate turbulence is in the control period. So if you've ever experienced moderate turbulence, you more than likely will experience severe turbulence by the second half of this century. And for a range of turbulence strengths, summertime turbulence will be as common as wintertime turbulence in the control period. So we know that in general, winter, the jet stream is stronger and therefore there's more turbulence. So we would expect summer to be as frequent as winter, and winter to be even more frequent than it is currently. And this just emphasizes the fact that flight planning may become more important in the future. And that's where we provide the motivation for trying to improve turbulence forecasting. So how do we currently forecast turbulence? Operationally, at the Met Office, they use a single turbulence index to produce a deterministic, so a single forecast of where they expect turbulence to be. And this is a shear turbulence index only, so it doesn't forecast convection. And then they have forecasters that produce these significant weather charts, where it shows convection, which is the squiggly lines. It shows where there's likely to be deep convection that might cause turbulence. So this is predominantly where you might experience turbulence and potentially a region to avoid. And then we also have the yellow dotted regions, and that's where they expect there to be moderate or greater turbulence. And then they also indicate the jet stream. So the jet stream being the fast-flowing river of air that I mentioned before. The green lines point out where the jet stream is and at what flight level and the wind speed involved. So the initial trial that we conducted was to compare 2 ensembles. So an ensemble forecast is multiple runs at the same time period. So if I'm forecasting for tomorrow, I would run a single forecast, then I would slightly perturb the model to forecast something slightly different. And then if I did this, for example, 12 times, as the Met Office Ensemble Forecast did, then I would get 12 separate outcomes, and depending on how similar those outcomes are, would tell you the confidence of what you expect will happen. So if we have this for 2 ensembles, so the Met Office Global and Regional Ensemble Prediction System, as well as the ECMWF, which is the European Centre for Medium Range Weather Forecasting, and their ensemble prediction system. So by comparing turbulence observations from a fleet of 747 and 777 aircraft, we can verify our forecast. So we produce a forecast and then verify it against real-world observations. And this is for a full year between May 2016 and April 2017. And we used the LROD and NAP Turbulence Index 1. And as I said before, this is the one that was used operationally by the Met Office already. So we used this individual diagnostic in this multi-model ensemble trial. So just for reference of the flight data that we use, this is a plot of a month's worth of data in May 2016 from the aircraft data that we have. So it shows you the coverage. We have great coverage over the North Atlantic and Europe, but then less so around the world and none over the Pacific. This is mainly due to the limited airline data that we have. Hopefully one day more airlines will provide this information, and then we can have more spatial coverage to help with forecast verification. But this is the example data that we have. So here's just a case study example. So each dot is a 10-minute segment of some flights that occurred, and where you have the orange dot, that is light turbulence, so where the aircraft observed light turbulence, and then the red dot is where the aircraft experienced moderate or greater turbulence. So in each of these panels, we have a slightly different forecast. So in the top left, we show the terrain. So you can see you've got Greenland to the west, Iceland to the east. And so this event occurred over the middle of the North Atlantic, and it was well away from mountains, and therefore we wouldn't expect it to be associated with mountain wave turbulence. In the top right-hand section, this shows convection. So you can see there's a little bit of red right at the bottom of the chart that shows where there's some deep convection, but there's no convection, so no thunderstorms around the turbulence event. And in the bottom 2 tiles, we show the ensemble forecast that we produced from the Met Office and the ECMWF. And you see that both forecast centers predict there to be turbulence in the area where turbulence was observed. So this shows that we have, because both models predict turbulence, we have quite high confidence that there was likely to be turbulence in that region. And as we see, the verification showed that there was turbulence in that. So that was a hit, and that's exactly what we would want to see when producing this turbulence forecast. But then a slightly different example is we see the 3 red dots over the Rocky Mountains in North America, in the United States. And we see, because it's occurred over mountains, this could be a mountain wave turbulence event, but and there's no convection as seen in the top right. And then both ensemble forecasts don't pick up a significant signal that there would be turbulence in that region. And this is one of the reasons why we would want to expand this trial to include convection and mountain wave turbulence as a forecasting predictor. But that's something that we'll come on to later. So this might be classed as a miss because our ensemble forecast system was unable to predict this mountain wave turbulence event. So how we measure the forecast skill is to plot a relative operating characteristic plot. So when we produce a forecast of turbulence, we categorize it whether it was a correct positive, so we forecasted turbulence and turbulence was observed. We forecasted turbulence and turbulence was not observed, so that would be a false alarm. We didn't forecast turbulence and turbulence was observed, that would be a miss. And then we correctly didn't forecast any turbulence, so that'd be a correct rejection. And then what this plot essentially shows is the forecast skill. the main point to take away is that the area under the line is a good way of measuring the quality of a forecast. So the higher the area under the curve, the more skillful the forecast is. And we see that for the most part, where we have the data and we're not just cutting off as a straight line, both the ECMWF and MoGREPS forecast pretty well compared to the multi-model ensemble, but the multi-model ensemble is very slightly more skillful. So the area under the curve is slightly larger, which suggests that the multi-model ensemble is a better forecast, but not significantly so. So it wouldn't meet any statistical significance standards, but it is a better forecast. And then a slightly different way of showing forecast skill is a relative economic value plot. And what you do is you assign a cost and a loss for whether you would have taken action or the loss if you didn't take action in a turbulence event, and then plot the value of this. And essentially what we say is that for any cost-loss ratio, so cost-loss ratio being high cost, whereas relatively little loss, or it's relatively inexpensive but would cost a lot if you were to get it wrong, would vary the cost-loss ratio. But if a forecast model is more valuable for all cost-loss ratios, then we would say that that model would be better. And what we can see here is that the multi-model ensemble and an optimized multi-model ensemble is above the individual ensemble forecast systems. So we would say here that the multi-model ensemble is more valuable to an end consumer than the individual ensemble forecast system. And therefore, that's why we'd say it's almost like a success. We're saying that this is better than an individual ensemble forecast. And this is a reliability diagram. The example would be if you forecast that there's a 1% probability of turbulence, then you would expect to observe turbulence 1% of the time. And we can see that all three ensemble forecasts are pretty reliable. So this is the single diagnostic ensemble. It is more skillful, but not significantly. But the multi-model ensemble is more valuable. And as we showed for that case study, we need to include other turbulence indices. So a convective index, maybe a mountain wave turbulence index, and other shear turbulence indices, because the LROD turbulence index is unable to forecast every type of turbulence. So that's when we move on to a multi-diagnostic trial. So multi-diagnostic, we use multiple forecasts of turbulence for different indicators, and then rerun the exact same trial. So using the same ensemble forecast systems, comparing the same flight data from the fleet of 747 and 777 aircraft for a full year. And this time we look at the LROD index, Brown index, and Richardson number. They're both shear turbulence forecasts. And then we also include a mountain wave turbulence index and convective precipitation accumulation, which we equate to deep convection, and therefore is a forecast of thunderstorms essentially. And what I've plotted here is essentially a rerun of the previous trial. So it's a single diagnostic multi-model ensemble. And we can see again, the multi-model ensemble has a higher area under the curve, which, as I said before, the higher the area under the curve, the more skillful the forecast. But using the significance bar, so that the whiskers of this plot show the 95% significance, it's not significantly better than a single model ensemble. And again, the ECMWF forecast comes out slightly more skillful for each of the individual diagnostics than the Met Office's forecast. And here again is a plot of that, just to show the area under the curve of the bold line, which is a multi-model ensemble, is slightly higher than each of the individual models, and therefore it is more skillful. So this is a plot to show the multi-diagnostic ensemble aspect. So the blue bar is a multi-diagnostic single model ensemble. So it's multiple, all 5 of the turbulence diagnostics for the ECMWF ensemble forecast system. The orange is the same. It's all 5 turbulence diagnostics for the Met Office's ensemble system. And then the green bar is a multi-diagnostic, multi-model ensemble. The 2 grey bars show the significance again. So we would want the light grey bar to be above both the blue and orange to show that it's statistically significant, but unfortunately we're unable to do that here. What we do show is that for this example, the Met Office is more skillful than ECMWF, which contrasts to what we showed before, where for the individual diagnostic, ECMWF performs better, but when combining diagnostics, Met Office performs better. And again, the multi-model ensemble performs better than both the individual ensembles. This is a value plot again, showing that the bold line generally is above both the dash and dotted line, showing that the multi-model ensemble is more valuable than the individual ensembles. And reliability again, generally reliability is good up until a point, just over 0.2% probability, where we start to under forecast turbulence. And this, I think, would require potentially, we've used a linear scale for probability, but you could use a non-linear scale and this might be able to flatten out that curve. But for simplicity, we kept it as linear, and that's why we see this under forecast at higher probabilities. So because we showed that the Met Office was a better ensemble forecast in a multi-diagnostic context, we hypothesized that this was because it had fewer ensemble members. So the ECMWF ensemble forecast system has 51 ensemble members, whereas the Met Office only has 12. So to understand whether ensemble size matters, so the number of members matters, we reduced the ECMWF to have the same ensemble size as the Met Office. And if we take the first 12 members, we can assume that each ensemble member is equally likely, and therefore we just take the first 12 members and then produce a forecast. And again, we see the Met Office is generally slightly worse for an individual diagnostic ensemble, but the multi-model ensemble is better than both individuals again. But when creating a multi-diagnostic ensemble, the Met Office outperforms ECMWF again. And as before, the multi-model ensemble is more skillful than both the individual ensembles. So to compare this, this is a plot where the circle is the 12-member ECMWF ensemble forecast. The diamond is the 51-member ECMWF ensemble, and the triangle is the Met Office. And we see that for an individual diagnostic ensemble forecast, the 51-member performs best, with the 12-member ECMWF and Met Office performing slightly worse. However, when we combine diagnostics, as we showed before, the Met Office outperforms the 51-member ECMWF, and actually the 12-member ECMWF forecast, when optimized, outperforms the 51-member ECMWF. So this result shows or suggests that fewer ensemble members in a multi-diagnostic, multi-model ensemble might be better than a higher number of ensemble members. And I think this requires more analysis as to why. Is there an optimum number of ensemble members? Is this that we haven't been able to optimize the 51-member well enough, and actually we can provide more forecast skill? That's something that we weren't able to answer in this study, but would be interesting to find out what the answer to that question is. So just to summarize, the multi-diagnostic MOGREPS ensemble is more skillful than the ECMWF, and the multi-diagnostic multi-model ensemble is more skillful than both the individual ensembles, which was the point of this study. We wanted to show that a multi-model ensemble is better at forecasting turbulence than an individual ensemble, which studies have already shown is better than a single diagnostic forecast. And actually, we showed that a reduced size ECMWF ensemble gives a more skillful result, and further work is required to understand why that might be, and if, again, as I say, there is an optimum number of ensemble members. So just to summarize what we've covered here, climate models can predict the location of clear-air turbulence. And then in the following study, climate change is set to increase clear-air turbulence globally in the future, with some regions such as the North Atlantic more than doubling. We also showed that the multi-model ensemble is more skillful than a single model ensemble, but not significantly so. But a multi-diagnostic multi-model ensemble is more skillful than that, with potentially a reduced size ECMWF ensemble giving more skill. So that's all I've got here. So I just want to say thanks again for inviting me on this talk, and yeah, I'll hand back to Anna.
Thank you, Luke. Can you all hear me? I presume you can. Very interesting, very dense as well. For some of us, we can definitely see that there's been a lot of work and a lot of number crunching behind all this research. And as I said, quite impressed with all the publications that have come out of all this work. I've got quite a few questions in the Q&A panel, so I'm just going to pose them to you. Hopefully I will do justice, trying to translate the comments that I'm getting here. I've got a couple of questions from Robin Ricks. These are related, so I'm going to read them both together. He says, aircraft are fitted with lap seatbelts and cars are fitted with 3-point inertia seatbelts. Would similar seatbelts as used in cars help? And he also says that since experiments at Farnborough, the RAF seats in transport aircraft face the tail. So would both of these measures, the car belts and the rear facing, help safety during heavy turbulence?
So I think this isn't necessarily a question that I can answer, because I've focused on the turbulence forecasting as a way of mitigating turbulence, and that sounds more like an engineering type question. But I would imagine, I think on some aircraft, for example, British Airways, I believe in business and first, they've introduced a 3-point seatbelt, but that doesn't mean that it would be better for turbulence necessarily. I think any seatbelt is better in severe turbulence. I'm not sure if turbulence is severe enough that it would require a 3-point harness, but I guess that's for the experts who are conducting those experiments to say. Yeah, I really wouldn't know and wouldn't want to speculate to answer that without seeing the evidence myself. So sorry.
Thank you. I've got another question. This is again probably 2 questions back to back. So again, I'm going to sort of read them together. And this is from Peter Fryer. He says, which metadata providers does British Airways use to provide data, and how prevalent are the METs, the pilot weather reports from the pilots in flight these days?
So in terms of British Airways, I am not 100% sure, because from what I understand, we recently went through a change. The contract that we did have was up earlier this year. So with everything that's happened with coronavirus, I'm not sure. I didn't keep up to date with what provider that we're now using. So I think there are quite a few different ones that you could use. I know the Met Office produces one. There's a new app-based system that uses some turbulence forecast that flight planners, pilots can basically plot their projected track and then overlay the turbulence forecast on top. And I'm not sure what underlies that turbulence forecast, but I can't remember the name of it. But if you would like me to find out, I'm sure I could, but I'll have to, I don't know off the top of my head is the answer. And in terms of pilot reports, they are quite prevalent. I know that they have to, if they've experienced turbulence, they have to report it. And it's one method of turbulence avoidance, for example, over the North Atlantic. If one pilot flying ahead of another experiences some turbulence, they can report this, radio back and say that there's turbulence here, and then the aircraft behind might be able to, depending on airspace travel restrictions, either change course, change altitude to try and avoid the turbulence. But they are available. But one thing that I would point out is that we didn't use pilot reports in our study because they can be unreliable. Firstly, because they spatially are not reliable, because if you enter turbulence, the pilots might have to take mitigating action, so then they don't have time to report the turbulence exactly where it happened. So then that might be 10, 15 minutes later where they report the turbulence, therefore mislocating the actual turbulence itself. And also it can be subjective. So it's based on a pilot's experience. They may classify an event as moderate or severe, but then a more experienced pilot who's experienced more turbulence might then categorize it as light or even less. So it is not necessarily a reliable way for us to verify the results, but it is definitely useful for in-flight, and it does happen.
So I guess a follow-up question from this one. Look, so obviously you're not only using pilot report of turbulence. So what else are you using? Are you using flight management, aircraft loads data? What is the other sources of information that you're using then?
So for our study, we used something called the derived equivalent vertical gust. So this is basically using an accelerometer that was fitted on board a fleet of 777 and 747 aircraft, and then measuring the vertical accelerations of the aircraft over the course of the flight. We can calculate, as an aircraft independent measure, the strength of the turbulence at the time. So there's another potential method, which is using the eddy dissipation rate, which uses a similar method of having onboard measures. But the important factor is that both of these aircraft are aircraft independent. So it doesn't matter what aircraft you're on, whether you're on a large aircraft and experience moderate turbulence, and then a smaller aircraft that would experience more severe turbulence within the same volume of air, the derived equivalent vertical gust or eddy dissipation rate would be the same. And that's based on these accelerometer measures on board the aircraft. So it gives a less subjective view of turbulence.
Yeah, makes sense. Another question here is interesting one. It says, is it assumed that turbulence will increase with altitude, or is it feasible that cruising above the 40,000 feet, modern aircraft have higher max altitudes? Could that be beneficial?
So what we found in our study was actually turbulence increased more at higher altitudes. So the higher the altitude, the more the turbulence increased. So it might not necessarily mean that flying higher would allow you to avoid the turbulence, because we're expecting turbulence to be more prevalent than in the pre-industrial control. But that isn't to say that, because it could be that there was less turbulence in the base and therefore the percentage change is higher at the higher altitude. So if you can fly even higher than 40,000 feet, I think the Concorde flew nearer 50,000 feet. It might just fly straight over and through all turbulence. So supersonic flight might be the answer. But yeah, I don't think flying above 40,000 feet would necessarily help, because turbulence isn't just the cruising altitude that we've studied here. It's prevalent throughout the atmosphere.
Fantastic, thank you. I've got another question. This is from Ellie McBrien. She says, as a flight crew, we often rely on turbulence information en route from the local ATC stations. She says ATC normally gather local information from other pilot reports in the area to pass on to us, which can be subjective and not necessarily accurate for our routing. So if the levels of turbulence are threatening to increase as much as you predict, do you think that there will be the possibility to share this better forecasting in real time directly to the flight crew?
I definitely think so, and I think that is one of the advantages potentially of having, for example, onboard connectivity, being able to send every updated forecast directly to the flight crew on board, rather than and having an image of where the turbulence is directly sent to the aircraft mid-flight. But also, I think there is potentially the technology for example, if we have these accelerometers fitted on an aircraft that does measure turbulence exactly when and where it happens, if that can then be, if every aircraft had it and every airline decided that they wanted to be part of a scheme, you might be able to collect and gather this data and then send it back real time to the airlines and flight crew behind to say, here is a reported case of turbulence. It's not subjective, it's not time delayed, it's real time. And if everyone did it, then we might be able to produce those kind of real time updates that maybe could give the flight crew enough time to be able to change either flight level, flight path, whatever it might be, to avoid the most severe turbulence. Or they might know that it's moderate turbulence, for example, and it's not going to threaten the safety of any passengers and crew, so just put the seatbelt sign on. At least if people are buckled down, then they'd be able to protect themselves more so than if they're just walking around the cabin. So I think there's definitely potential for that.
Good. I think Ellie would be probably relieved to hear this then. Another question, and this is a question that has come a number of times, so I'm going to try to sort of rephrase it. Basically, it seems like if climate change is having a significant influence on the North Atlantic routes, right? This is the world's busiest flight corridor. I think there are over 3,000 flights crossing the pond on an average day. I guess the question is, climate change clearly is having an impact. Is it possible perhaps that some of these routes may be seasonally unsafe to fly by mid-century? Is it perhaps possible to think that climate change can have an impact on routes that airlines are flying? Are you seeing any of these already?
So I would say not make it unsafe to fly during seasons, because one thing to point out is that we currently only expect moderate or greater turbulence to be in 1% of the atmosphere. So it's a very, very small proportion of the total atmosphere. So I wouldn't say that there would be a blanket, it's unsafe to fly throughout the entire season or proportion of the airspace, but that's why I think we need to have better forecasts, because what might happen is if we have these better forecasts and then we say we expect there to be some severe turbulence in this portion of this region, it might be, let's say, over Greenland, for example, there's an extremely high likelihood of severe turbulence. Flight planners will know ahead of time, basically just to divert south. Yes, it might not be on the Great Circle route, so flight times might be slightly longer, but if you just almost avoid that entire region based on the forecast, then you would be able to avoid it no problem and then keep the airspace open. I think the best way to mitigate that is to have better forecasts. And we believe that this method that we've come up with is a better way to do that.
Good. Makes sense. Another question is, unrelated and related to the work that you've been doing. The question says, why do you only take data from the 747 and 777 aircraft and not Airbus aircraft? Is this related to the data supplied, accessibility to data, or the ability to get the derived values?
So I believe we only had it on 777 and 747 aircraft because they were the aircraft where the technology was installed at the time. And I had previously spoken to someone who worked for Boeing, and they said that they were installing these more regularly in new aircraft. So the data was going to be there. So I don't. It's possible that Airbus, for example, would be able to install this technology, but at the time we only had 747, 777 aircraft that had it installed. So it was just a limiting factor, not because it was Boeing and not Airbus. It was just that was the data that we had at the time. So that was all we could use.
The access to data, right, is always the bottleneck when you are doing research. Absolutely. I really relate to that, Luke. Another question related again to the work you've been doing, the research you've been doing. Can you discuss the role of machine learning in making some of these predictions?
Yeah, I think machine learning would be extremely valuable, especially in optimizing some of these forecasts, for example. So we use quite a simplistic, iterative method for optimizing our forecast. But if you could produce some machine learning algorithm that could optimize the forecast better, I think that would be very useful. I think the technology is getting so good now that definitely machine learning is an option. But obviously we were unable to do that during my time. But I definitely think it's something that could be useful in the future. Yeah.
So you think that improved, like more skillful CAT forecasting offset the probable doubling up of turbulent levels over the North Atlantic, or can we expect to actually experience more severe CAT as passengers and crew?
Well, I guess the theory is we shouldn't expect to experience more turbulence because our forecasting has got better. So yes, there will be more turbulence in the atmosphere, but if we're forecasting better, then the everyday passenger wouldn't notice. Potentially, that would be the main goal, I would have thought. So yeah, hopefully not, but it becomes more difficult, I think, to avoid it, especially if the airspace is, for example, the North Atlantic is as busy as it is now. You might not be able to avoid it because you can't move because you're surrounded by the aircraft.
Yeah, makes sense. One question from Tony Gee. He says, PhD applied physics ready in 1974. Let me see if I do justice to this. I'm going to read the question slowly. So he says the UK gliding height record is over 37 kilofeet over the Grampians near Aberdeen, where they experience lift rates of 11 knots. About 350 miles per minute at heights of 20 kilofeet. That's about 10 times the terrain heights and impingements of regular domestic flights to Aberdeen and Inverness. Shouldn't you study local data in the lee of parallel valleys as a race downwind of the Great Glen?
I would suggest probably yes. I think doing more local studies would definitely be better. And I think if you did a local study, then you could use higher resolution models to better model turbulence and all these effects. Yeah, I would agree with that. I think definitely more local studies. I guess the question is, does it impact enough that the time spent on the studying and researching would be I guess it's a value reward type question, but I think it'd definitely be interesting, and I think you get a lot out of it if you were to do a study like that. And I know studies have been done particularly around the Colorado, Denver, Rocky Mountains region for similar things of what is a local impact on turbulence around the local region of the Rocky Mountains. But yeah, it's not to say that we shouldn't do one here.
We've got a couple of minutes and not much more than this, and I can see lots of questions that probably won't have time to ask you. Again, I just want to take you. You say you've done a little bit of storm chasing while you were in the US. I mean, that must have been quite exciting. Was this just for pure research, or was just for the I guess the thrill of chasing something awesome in nature with loads of power and lots of beauty?
It was most definitely for fun, no research involved. The university that I was studying at, the University of Oklahoma, is world-renowned as a storm chasing university. So there's an extremely famous storm chaser called Reed Timmer, he was one of the people that inspired me to get into meteorology in the first place. He did a PhD at the University of Oklahoma, and he is world renowned as a storm chaser. But for me, it was me and my friends. We got a radar system, drove around, used our knowledge of where we expected the storms to be, and unfortunately I was unable to see a tornado, although I was within 1 mile of one that was unfortunately quite devastating. So although I didn't see it, I was near enough that I was terrified. But yeah, it was a thrill, but I probably won't be doing it again.
I think it's wonderful that you've managed to combine your passion and really enjoy very much. It really shows that you enjoy what you're doing, Luke, and it's contagious. I think it's reassuring to know that turbulence is not a typical cause of airplane crashes. It's not something that we should be really too worried about. It's also quite reassuring that there are people like yourself, using your great mind to help us understand and forecast and better plan ahead. So again, Luke, thank you very much for being with us. As I said, I've got questions that I've not been able to ask you, but I'm really delighted to have had you with us. I hope that we can see you around in the Royal Aeronautical Society Heathrow branch again. And again, thanks for your time. So I'm just going to thank you. I'm just going to, put the spotlight back onto William. I think he might want to give us a little bit of advance warning about what's coming up in November, in the November lecture. Luke, thank you very much, and we hope to see you soon again. Thank you.
Everyone, on behalf of the chair, Peter Fryer, who is also online with us, but due to technical issues, he's unable to host himself. So on his behalf, I would like to thank Anna and Luke. Anna for hosting this lecture, and Luke for giving us this fascinating lecture. Looking at November, we have invited the founder and CEO of Zero Avia, which is a company based in California and have an ops center in Cranfield University, who you may have actually seen quite a lot of news coming out recently about their electric aircraft and their hydrogen-powered aircraft. So we will be inviting the founder and CEO of Zero Avia in our November lecture, which currently is penciled down in potentially 19th of November, but we are still tweaking the final date. So please do visit our website, aerosociety.com/Heathrow for the latest information, or go to our event registration platform, which is tiny.cc/RAESLHR. So ladies and gentlemen, thank you for joining us today, this Royal Aeronautical Society Heathrow branch webinar. I hope you enjoy it as much as we do. So before you go, I would like to remind you to look at our social media platforms, Twitter, Facebook group, LinkedIn group, and most important, our YouTube channel, which contains all our past recordings, the recordings of our past lectures and webinars, which you will enjoy, as well as some webinars and conference recordings of the main society. Just go to search RAES Heathrow branch on the above channels, and you will find us on there. And please do visit aerosociety.com/Heathrow for further information about our latest events. And thank you for your.
From across the globe, from the center of aerospace, and now to you.
Thank you for downloading from the Royal Aeronautical Society. If you enjoyed this content, please consider showing your support for the Society. Share a link to this presentation by email or on your favorite social networks. If you have an interest in aerospace, consider the professional and personal benefits of membership. Visit www.aerosociety.com.